characteristic equation. So once you know the stress tensor, then you can also calculate the mean stress, and you can also calculate the deviated stresses, because we have already seen how to do deviated stresses from the stress tensor. Okay, so the next one is it was found experimentally that a certain material does not change in volume when subjected to an elastic state of stress. Okay, and for such materials, calculate the Poisson's ratio. So this is basically a worked out example in many textbooks. Okay, so it's quite simple. So try to understand what is given, and this question has 2 marks for the assignment. So write down the material properties, then try to show that the Poisson's ratio so does not change in volume means what? A material does not change in volume. Means initial volume is equal to final volume. The material undergoes deformation, but the total volume, there is no change. So initial volume is the final volume. So when a material is okay, so material does not change in volume. So this means that the initial volume is the final volume. Okay, so that means change in volume is 0. Right? So we know the material property relation. So the volumetric strain K so volumetric modulus of elasticity so K can be written as Young's modulus over 3 times 1 plus 2 Poisson's ratio. So this is 2. So this is the material property relationship K. And we know this is equivalent to the mean stress over the volumetric strain. Okay, so if we take this portion, so we can write Young's modulus multiplied by volumetric strain. Okay, we can write 3 sigma m into 1 plus 2 mu. Okay, so the material does not change in volume. So implies the volumetric strain is 0. So now you can write from this expression so find out what is new value from here. So what is your answer? Yes. -2. How about others? -1/2. So it is simply 0.5. I'm sorry, this one will be, what is the formula here? It is 1 plus 2 nu or 1 minus 2 nu?
1 minus.
I think
1 minus.
I wrote the formula wrong. So here this one should be negative. So therefore you get the positive value here. All right. Any doubts? So this question has 2 marks, so you will get should get 2 out of 2 for this. Next, I go back to the concept of stress and strain, engineering stress, engineering strain. So we defined that engineering strain is change in length over original length. Okay. Then true strain is simply a natural logarithm of the original transform length over original length, L over L naught. Okay, so that is the true strain. Engineering strain is delta L over L naught. Okay, so can you do this question? So determine the engineering strain E and true strain epsilon in these three cases. So when it is as an extension from L to 1.02 L. So engineering strain E can be, so this is the final length. So final length in this case is 1.02 L minus L over L. Okay, so how much is this? So here the engineering strain is 0.02. So what is the true strain? So true strain will be epsilon. I write epsilon is ln 1.02 L over L. So how much you get here? So you can cancel L and find out the value of natural log 1.02.
0.019.
So you can see the value is very close, 0.0198. So when the deformation is small here, so both the engineering strain and the true strain, they are very close, they are equal. Okay. Now similarly, when you have a compression from a height h to 0.98 h,